All right, so the plan for today is to continue our discussion of score-based models, and we'll see how they're connected to diffusion models, and we'll kind of like see some of the state-of-the-art stuff that currently is being used to generate images, videos, some of the things we've seen in the very first introductory lecture. So, brief reminder, this is kind of like the usual roadmap slide for the course. Today we're talking about diffusion models or score-based models. You can think of them as one way of defining this model family by parameterizing the score and then learning the data distribution by essentially using some kind of score matching loss. And we've seen that, that's kind of like the key underlying idea is that to represent the probability distribution, we're going to use a neural network which is vector valued. So for every point, it gives you a vector, and that vector is supposed to represent the gradient of the log likelihood at that point. And so you can think of it as a vector field, like the one you see here, that is parameterized by some neural network. And so as you change the weights, you get different vector fields. And we've seen that it's possible to fit these models to data by doing score matching. And so we've seen that the kind of machinery that we talked about in the context of energy-based models can be applied very naturally to these settings. And so there is a way to fit the estimated gradients to the true gradients by minimizing this kind of loss, which only depends on the model. This is the thing we derived by doing integration by parts. And it's a principled way of fitting the model. The issue is that it's not going to work in practice if you're dealing with high-dimensional settings because of this trace of the Jacobian term that basically would require a lot of backpropagation steps. So it's not going to work if you're trying to, say, model images. And so in the last lecture, we talked about two ways of making score matching more scalable. The first one is denoising score matching, where the idea is that instead of trying to model the score of the data distribution, we're going to try to model the score of this noise-perturbed data distribution. And typically, the way we obtain this noise-perturbed data distribution is by starting from a data point and then applying this kind of perturbation kernel, which gives you the probability over, given that you have a clean image X, what is the distribution over noisy images X tilde, and it could be something as simple as let's add Gaussian noise to X. And it turns out that estimating the score of this noise-perturbed data distribution is actually much more efficient computationally. And so the usual kind of score matching loss where you do regression, some kind of L2 loss between the estimated score and the true score of the noise-perturbed data density, that's kind of like the key difference here. We're no longer estimating the score of P data, we're estimating the score of Q sigma. It turns out that it can be rewritten in terms of the score of this transition kernel, perturbation kernel, Q sigma of X tilde given X, which is just, let's say, a Gaussian. And so, in the case of a Gaussian distribution, this objective function basically corresponds to denoising because basically the score of a Gaussian is just like the difference from the mean, essentially. And so you can equivalently think of denoising score matching as solving a denoising problem, where what you're doing is you're sampling a data point, you're sampling a noise vector, and then you're feeding data plus noise to the score model as theta. And the goal of the score model is to try to estimate Z, essentially, which is the amount of noise that you've added to the clean data X. And so there's this equivalence between learning the score of the noise-perturbed data density and performing denoising. And as you see, this is much more efficient because we no longer have to deal with traces of Jacobians. It's a loss that you can efficiently optimize as a function of theta. And so the pros is, it's much more scalable. It has this intuitive kind of correspondence to denoising, meaning that probably architectures that work well for denoising are going to work well for this kind of score estimation task. The negative side of this approach is that we're no longer estimating the score of the clean data distribution. We are now estimating the score of this noise perturbed data density. And so we're kind of shifting the goalpost here because we're no longer estimating the score of the true data density, but we're estimating the score. Even if we're doing very well at solving this problem, even if we can drive the loss to 0, we don't overfit, everything works well, we're no longer estimating what we started out with, but we're estimating this noise perturbed data density score. And then we've seen the alternative is to do some kind of random projection, and that's the slice score matching approach, where essentially instead of trying to match the true gradient with the estimated gradient at every point, we try to just match their projections along some random direction v. And so at every point, we sample a direction vector v based on some distribution. We project the true score, the estimated score at every point. After the projection, you get scalars, and then you compare the projections. And if the vector fields are indeed the same, then the projections should also be the same. And it turns out that, again, this objective function can be rewritten into one that only depends on your model, kind of the same integration by parts trick. And now this is something that can be evaluated efficiently, can optimize efficiently as a function of theta, because essentially it only involves directional derivatives. And so it's much more scalable than vanilla score matching. It also estimates the score of the true data density as opposed to the data density plus noise. But it's a little bit slower than denoising score matching because you still have to take derivatives basically. So that's sort of like where we ended kind of like last lecture. And then the other thing we talked about is that how to do inference. And we said, well, if you somehow are able to estimate the underlying vector field of gradients by doing some kind of score matching, then there are ways of generating samples by using some kind of Langevin dynamics procedure where you would basically, these scores are kind of like telling you in which direction you should go if you want to increase the probability of your data point. And so you just follow these arrows and you can generate samples basically. And what we've seen is that this didn't actually work in practice, this variant of the approach. It makes sense, but it doesn't work for several reasons. One is that, at least for images, we expect the data to sort of like lie on a low-dimensional manifold, meaning that the score is not really a well-defined object. We have this intuition that we're not expecting to be able to learn accurate scores when we're far away from the high data density regions. Kind of like, if you think about the loss, it depends on samples that you draw from the data distribution. Most of the samples are going to come from high probability regions. When you're far away, you have an object that looks nothing, let's say like an image. You've never seen these things during training. It's unlikely that you're going to be able to estimate the score very accurately. And that's a problem because then kind of Langevin dynamics depends on this information to find high probability regions. And so you might get lost and you might not be able to generate good samples. And then, we've seen that there are issues with the convergence speed of Langevin dynamics. It might not even converge. If you have zero probability regions somewhere, it might not be able to go from one region of the space of possible images to another one. And so that's also sort of like an issue. And so what we are going to see today is that there is actually a very simple solution to all of these three issues that we just talked about. And that basically involves adding noise, adding, let's say, Gaussian noise to the data. And to see this, we notice that, well, one issue is that if the data lies on a manifold, then the score is not really defined. But the moment you add noise to the data, then it becomes kind of like supported over the whole space. Noisy data, you're adding noise, so any possible combination of pixel values has some probability under this noise perturbed distribution. And so even though the original data lies on a manifold, the moment you add noise, you fall off the manifold and it becomes supported over the whole space. Score matching on noisy data will allow us to basically estimate the score much more accurately. This is kind of like some empirical evidence showing, if you try to do score matching on CIFAR10 on clean images, the loss is very, very bumpy. You're not learning very well. But the moment you add noise to the data, tiny little amount of noise to the data with some tiny little standard deviation, then the loss converges much more nicely. It solves the issue of the fact that score matching is not accurate in low data density regions. I remember kind of like the intuition was that most of your data points are going to come from, let's say if your data is a mixture of two Gaussians, one here and one here, most of the data will be, the samples that you see during training are going to come from this region or this region, the two corners where the data is distributed. And as a result, if you try to use data, fit a score model, there is a true score model in the middle, there is a true score in the middle, there is an estimated score on the right. It's going to be accurate around the high data density regions. It's going to be inaccurate the moment you go far away. But if you think about adding noise, again, it's kind of like a good thing for us, because if you add noise to the data, then kind of like the samples of the noise perturbed data densities are gonna be, again, kind of like spread out all over the space. And so what happens is that now, if you think about where you're gonna see your samples during training, if you add a sufficiently large amount of noise, the samples are gonna be kind of like all over the space. They're gonna be kind of just spread around the whole space. And what this means is that if you're willing to add noise to the data and you add a sufficiently large amount of noise, then we might be able to estimate the score accurately all over the space. And now, of course, this is good because it means that we might be able to get good information from our Langevin dynamics sampler. Like if we're relying on these arrows to go towards high probability regions, Langevin dynamics will probably work if we do this. The problem is that we're no longer kind of like approximating, we're no longer, if you do Langevin dynamics over these estimated scores, you're going to be producing samples from the noisy data distribution. So you're going to be generating images that kind of like look like this instead of generating images that look like this. So that's kind of like the trade-off here. Yes, we're going to be able to estimate the score more accurately, but we're estimating the score of the wrong thing.
Basically, we talked about score estimation being the same as denoising. So I guess how is this different than that concept? Because we showed that score matching is equal to denoising. So to me, I'm a bit confused that we're just adding noise to the data. So what are we doing differently, maybe?
So before, what we were doing is we were estimating the score of the noisy data distribution. And so here, if you were to do this, yeah, you would be using denoising score matching. You would solve a denoising problem. You will learn the score of the noisy data distribution. Now you follow that score, and you're producing noising samples.
I see. So if we followed what we did, we would get noisy images.
We would get noisy images. That's the problem. Yeah, that's kind of like the trick. So on the one hand, you'd like sigma, the amount of noise that you add, to be as small as possible, because then you're learning the score of the clean data. So presumably, if you follow those scores, you're going to generate clean samples. On the other hand, if you do that, we're not going to be expected to learn the score very accurately. And so that's the dilemma that we have here, basically.
So it's essentially the difference between this and denoising score matching, that denoising score matching, we are putting noise on the real data samples and estimating that noise sample. But eventually, we're going to learn the new data sample if the noise is small. But here, we are kind of estimating, like, we're using the noise data samples from the first case, and if we're using denoising score matching, we're going to be adding noise to the noise samples. And then
No. Actually, you could use denoising score matching to estimate the score. In fact, that's what we would end up doing. So you could, if you were to use denoising score matching, you would take data, you would add noise, you would solve the denoising problem. What you end up learning is the score of the perturbed data density. So you end up learning this, but that's not this, which is what you wanted. It's not the score of the clean data density. So in particular, if you were to then follow those scores, those that you have here, you would produce samples that, according to the noise perturbed data density, so that in particular the images would look like this, not like this.
Are you saying this is equivalent to just doing denoising score matching?
So I haven't said how you do this. You could, I'm saying you could even do slice score matching here, or vanilla score. You could do slice score matching, for example, not vanilla, but you could do slice score matching here to estimate this. Denoising score matching would be a much more natural choice because it's faster and it automatically gives you the score of a noise perturbed data density. So here I'm just saying, even if you were able to estimate the scores, they are not what you want. Using denoising score matching would be a very natural way of estimating the scores, and that's what we're actually going to do.
So you're saying how like real data lies on the low-dimensional manifolds? Can you like say that in different words? Or what does it mean about like the real-life data that this looks like? What does that mean? How does it even work? What is that?
The manifold?
Yeah.
Yeah, it basically means that, like, if you recall from the last slide, we were saying, okay, if you were to do a PCA of the data and you keep a sufficiently large number of components, you reconstruct the data almost perfectly, which basically means that the different pixels in an image, they are not linearly independent. They kind of like, once you know a subset of them, you get all the others automatically, which basically means that the images lie on some kind of plane, essentially, which is sort of like what I'm visualizing here as with this shape. So not all possible pixel values are actually valid in the data distribution, essentially. There is some kind of constraints, which you can think of it as encoding this kind of curve, and all the images that we have in the data, they lie on this surface or this curve in a high-dimensional space. And so the score is not quite well defined, because what does it mean to go off the curve? Then kind of the probability is 0 the moment you go off the curve, and so it can explode, basically.
How does that work?
Once the moment you add noise, then basically any combination of pixel values is valid, right? Because there's always some probability of adding the right amount of noise such that that combination was possible. So if you imagine data that lies on a plane or that kind of surface, and then you add noise, you're kind of like moving the value by a little bit, and then it no longer lies on that plane or no longer lies on the surface. So you're breaking that constraint that held for the real data no longer holds for noise perturbed data. And that helps estimating the gradient more accurately.
Like real data, if it lies on a low-dimensional manifold, then like there are points that will just never occur. But then here, like when you're adding like such small amounts of noise, it still feels like there would be like a type of like low data problem where like any like really far out random assortment of pixels is like never gonna, like basically never gonna occur, even if it has some very minimal probability. Yeah. So is there like, or do we see, is it like basically a too small amount of noise that you do like this amount that like nothing really changes from adding more noise? Yeah, so noise does become more stable, but you do have this problem that, as you said, if you add sufficiently small amount of noise, you know, it's gonna be more or less, like there is not really a discontinuity. So yeah, you add a very small amount of noise, your noise perturbed data distribution is very close to what you wanted, so that's great, but you're not really solving the problems that we have here, basically. That's kind of like what I have in the next slide here. That's sort of like the question, how much noise do we want to add? Do you want to add a very little small amount of noise? Do you want to add a lot of noise? There is kind of a, if you think about, you know, the different amount of noise that you can add, you're going to get different sort of trade-offs. You can imagine that, you know, there is the real data density, there is the real scores, and if you try to estimate them using score matching, there's going to be a lot of error, kind of like in this region, as we discussed. And then you could say, okay, now I'm going to add a little bit of noise, so I'm no longer estimating the right thing, so there's going to be a little bit of error everywhere because I'm estimating noise perturbed scores instead of true scores. But my estimation starts to become a little bit better. And then you can add even more noise, and then at some point, kind of like you were doing a great job at estimating the scores,
but you're estimating the scores of something completely wrong because you added too much noise to the data. And maybe that's the extreme where you add a ton of noise, you've completely destroyed the structure that was there in the data. So what you're estimating has nothing to do with the clean images that you started from, but you're doing a very good job at estimating the score because it becomes very easy. So those are the things that you need to balance. We want to be able to estimate the score accurately, and so we would like to add as much noise as possible to do that. But at the same time, adding noise kind of reduces the quality of the things we generate because we're estimating the score of a noise perturbed data density. So we're no longer estimating what we wanted, which is the thing that we have up here, but we're estimating the score of a data distribution added with a lot of noise added.
So the denoising score matching thing, so that is just doing the first example, or that is what it was restricted to?
Denoising score matching can estimate any of these. You can use denoising score matching to estimate the score of any of these slices. But it's going to perform, it might become very bad, sort of like if the amount of noise that you add is very small. And so that's kind of like what you see here. Well, this is maybe the clean score. Or maybe this is a little bit of noise. Denoising score matching is not going to work very well.
So the denoising score matching is a technique that you can use to estimate the scores for any given thing. But
for any amount of noise.
We're actually changing the points, or like by adding noise, we're getting much more points.
No, so denoising score matching is a way of estimating the score of a noise perturbed data density with any amount of noise that you want. The question is how much noise you want to add. You'd like to add as little noise as possible because you want to estimate something close to the real data. But the more noise you add, the better estimation becomes. And so that's kind of like the problem, that you want to trade off these two things, and it's not clear how to do that.
Like when we add little noise, it's kind of we're dealing with a function that has discontinuity kind of feature, so that if you do like perturbation, kind of figure out the gradient, it's very easy to overshoot and undershoot, and then we sort of make the function smoother, so that we easy to find the gradient, but it's not accurate anymore.
Yeah, because you're estimating the gradient of the wrong thing. Yeah. So this is perhaps another way to think about it. Like imagine that somehow the data lies on this curve, and this is just like a curve in a 2D space. Most of your samples are going to be close to that thick line that we have here. What's happening? And so if you were to estimate the score far away from the black curve, it's going to be fairly inaccurate. Then you can imagine, okay, let's add a lot of noise, sigma 3. Then most of the samples are going to be, kind of like pretty far away from the black curve. And so we're going to get pretty good sort of like directional information when you're far away from a clean sample, but it's going to be inaccurate the moment you get closer to the real, where the real data lies. And then you can imagine a setting where you have a kind of like a ensemble of different noise levels. So you're not just considering a single noise level, but you're considering many of them. And so that you are able to get good sort of like directional information, both when you're far away and when we're a little bit closer and a little bit closer to the real data distribution. And that's kind of like the main underlying idea of a diffusion model or score-based model. The key idea is that we're not just going to learn the score of the data, or we're not just going to learn the score of the data plus a single amount of noise, but we're going to try to learn the score of the data perturbed with different kinds of amounts of noise. That's sort of like the intuition. And so specifically, we're going to consider different amounts of noise, sigma 1, sigma 2, all the way to sigma L. And we're going to use something called annealed Langevin dynamics to basically generate samples. And the basic idea is that when we start, when we initialize our Langevin dynamics procedure, there's probably going to be very little structure in the samples. They don't look like natural images. And so what we can do is we can follow the scores that were estimated for the data distribution plus a lot of noise. And for a little bit, if you were to keep running this thing, then you would be able to generate samples from the data distribution plus a lot of noise, which is not what we want. But what we can do is we can use these samples to initialize another Langevin dynamics procedure where we've decreased the amount of noise by a little bit. And then you basically keep running your Langevin dynamics procedure following the scores corresponding to the data density plus a smaller amount of noise, sigma 2. Then you decrease it even more, and you initialize, because you got closer and closer, kind of like to the high data density regions. Then we know that now we are starting to see more structure in the data, and so we should follow the score for the data density plus, let's say, a very small amount of noise. And then again, you kind of like follow the arrows, and then you're generating samples that we actually, like the ones we actually want. Because at this point, we kind of like get the best of both worlds, because at the end of this procedure, we're generating samples from data plus very small amount of noise. But throughout the sampling procedure, we are always kind of like getting relatively accurate estimates of the scores because we are considering multiple kind of noise scales. So at the very beginning, where there was no structure in the data, we were following the score corresponding to data plus a lot of noise. And then as we add more and more structure to the data, because we're moving towards higher probability regions by following these arrows, then we can afford to reduce we basically consider the gradients of data that was perturbed with smaller amount of noise. And this procedure will kind of like get us the best of both worlds, because Langevin dynamics is never lost. We're always following a pretty accurate estimates of the gradients. But at the same time, at the end, we're able to generate samples for a distribution of data plus noise, where this noise level sigma 3 can be very, very small. And so the final samples that you produce are going to be almost clean.
Is there any study on how many different noises and what the sequence decay should look like?
Yeah, so typically people use 1,000. That's the magic number. But then we'll talk, in the second part of the lecture, we'll talk about an infinite number of noise levels. So the natural way to do things is to actually consider continuous number of noise levels, an infinite number. And that's kind of like gets you the best of a lot of structure, a lot of interesting sound. So that's sort of like the intuition. And you can see here another example of what happens if you were to just run Langevin dynamics. It kind of like has this problem where you're seeing too many particles down here because it doesn't mix sufficiently rapidly. And even though there should be more probability mass up here, meaning that more particles should end up here, there's kind of like too many down here. Because the arrows are basically, you're not estimating things accurately. And if you do annealed Langevin dynamics, so you use this procedure where you run multiple Langevin dynamics chains corresponding to different amounts of noise, then it ends up giving you the right sort of distribution where you see there's many fewer particles down here, representing the fact that there should be less probability mass sort of down there. And here's another example kind of showing this, but let me skip. So what does it mean in practice? What it means in practice is that in order to do this, you need to be able to estimate the score, not just of the data density, not just of the data density plus a certain fixed amount of noise, but you need to be able to jointly estimate the score of the data plus different amounts of noise levels, various amounts of noise levels. So you need to be able to know what is the score of data plus a lot of noise. You need to be able to know what is the score of data plus a little bit less noise, all the way down to a very, very small amount of noise added to the data where it's almost kind of like the true data density. And that's fine, because if you do annealed Langevin dynamics, even though this score is only ever going to be estimated accurately close to the high data density regions, we still have that problem. Like this score here is not going to be estimated accurately everywhere. It's only ever going to be estimated accurately when you're very close to, let's say, a real image. But that's fine, because we're using this Langevin dynamics procedure, and we're only going to use this score model towards the end of the sampling, where we already have a pretty good guess of the kind of images we want. While this score here, which is data plus a ton of noise, is going to be estimated pretty accurately everywhere. It's going to be good at the beginning of the sampling, but we don't want to just keep following that because we want to be able to sample from something close to the clean data distribution. And so to make things efficient, what we would do is we would have you could potentially train separate score networks, one for every noise level. If you have, let's say, 1,000 noise levels, that would mean 1,000 different neural networks, kind of like training, each one being trained on a different kind of vector field. To make things more efficient in practice, what you can do is you can have a single neural network that takes an additional input parameter sigma, which is basically just the amount of noise that we're considering. And this single neural network will jointly estimate all these different vector fields. So when you fit in a large value of sigma here as an input, then the network knows that it should be estimating the vector field for, let's say, data plus a lot of noise, while when you fit in as an input a small value of sigma, then the network knows that it needs to estimate the vector field for a data density plus a small amount of noise. And so this is just basically a way to kind of make the computation a lot more efficient because we have now a single model that is trained to solve all these different estimation problems. It's going to be worse than just training 1,000 separate models, but it's going to be much more efficient because we're just training a single neural network at that point.
In this case, we're learning a vector field, not a probability distribution, right? But when you do the score matching for energy-based models, in that case, are we learning the solution to an ODE that has a closed form solution? Are we implicitly assuming that because we're taking a gradient of a probability distribution instead of just learning a vector field?
So so what we're learning here, so these vector fields are not necessarily conservative unless you parameterize the network in a certain way. You could potentially parameterize the network such that it's the gradient of an energy function. Actually, it doesn't hurt performance too much if you do that, but it doesn't actually seem to help. So in practice, you can just use a free-form kind of neural network that goes from, say, images to images, and that's not a problem. But you're right that it's not necessarily the gradient of a potential of an energy function, and so weird things can happen. Where if you follow a loop, the probability can go up or down, even though if there was really an underlying energy, it shouldn't change, right, the probability. So that could be a problem. But in practice, it works. Yeah?
Given the noise level, you can generate multiple perturbed data points with one real data point. So is that a hyperparameter they can choose?
The number of noise levels, is that the question? Whether that's
Given the noise level, you can still generate multiple data points with one real data point.
So you mean when we run the Langevin procedure, or?
Well, you generate the training data for the score function.
Yeah, you can generate. So we haven't talked about how we actually learn it. Right now, I'm just saying, what does the model look like? So the model is going to be a single neural network that will try to jointly estimate all these scores. How do we actually learn it? We're going to learn it by denoising score matching. So there's going to be this noise conditional score network, which is going to be a network that jointly estimates all this vector field of scores. And how should we train this? You could do slice score matching. It's much more natural to just use denoising score matching. Since denoising score matching already gives you the score of a noise perturbed data density, you might as well directly use that. So since we were trying to model scores of data plus noise, we might as well directly use denoising score matching because that's a little bit more efficient. And then the loss function is going to be kind of like a weighted combination of denoising score matching losses, because we want to jointly solve, let's say, 1,000 different tasks. And so the loss function might look something like this, where we have this noise conditional score network that takes as input a data point and a noise level and tries to estimate the score of the data distribution perturbed with that noise level at that point X. And we want to train this score network to perform well across different noise levels. So if you have the L noise levels, this noise network, this noise conditional score network should be able to solve all these different regression problems as well as possible. And so there is a lambda sigma I parameter here that basically controls how much you care about estimating accurately the scores at different noise levels.
Since the data is already perturbed now, we don't add an additional perturbations.
Yeah, so the loss would look like this. So the data is clean, as you said, and then you add noise corresponding to the sigma that you care about, and then you try to denoise that data point. And so if you think of it from the denoising perspective, we're not just learning to denoise data that has been perturbed with a fixed amount of noise, but we're basically learning a family of denoisers, each one working with different amounts of noise. So there is a denoiser that works when the data is corrupted with a very large amount of noise, and there's going to be a denoiser that works when the data is corrupted with a smaller amount of noise, all the way down to almost no noise being added to the data. And these are different denoising problems, and equivalently corresponding to estimating the scores of different noise-perturbed data distributions.
No longer kind of estimating the real samples.
Yeah, so when the noise is very large, basically denoising is very hard. If I add an infinite amount of noise, then basically all the structure in the original data is lost, and the best you can do is to basically output the average image, essentially, right? That's the only thing you can do. There is no information in X tilde about X, and so the best thing you can do is to basically, if you're trying to minimize an L2 loss, is to predict the mean. And you can imagine that if that's the only thing you have, you're not going to be able to generate good images. But because you know also how to denoise images with less amounts of noise, then if you know all these score models, then you can do that annealed Langevin dynamics procedure, and you can actually generate clean images at the end.
You said we can customize the lambda function to like assign weights, but from a practical standpoint, what sort of a lambda are we looking for?
So yeah, we'll get to what lambdas make sense. In theory, like if you had infinite capacity, this model is arbitrarily powerful. It doesn't even matter because it could sort of solve perfectly each task. In practice, it matters with which kind of how you weight these different score matching losses. We'll get to that. And yeah, so but the loss function basically looks like this. It's a mixture of denoising score matching objectives across all the different noise levels that we are considering.
Would I be correct in saying that, like, if you have different noise levels, then would the gradients be in some way related by some scaling factor? Because the general direction is the same. So to me, I'm a bit, I guess, like, why can't we just learn one model and just scale it? Because like kind of like learning rate. So like, you know, if you're far away, try to estimate it from, like, you know, try to get an estimate of the gradient, just scale it and just by a big amount and move in that direction. And as you get closer, just, you know, taper it down so that you know you'll converge. So why not do something like that? Because if you assume a Gaussian shape, then I assume that we should be able to scale gradients also, or scale the score, I mean.
So it's not simple. So it's true that they are all related to each other. So in theory, if you know the score at a particular noise level, you can in theory recover the score of different noise levels, but it's not just the scaling. So there is something called the Fokker-Planck equation. And if you were to solve that equation, which is just a PDE at the end of the day, but if you were able to solve that PDE, that tells you basically how the scores are related to each other.
So that's deterministic, but intractable, I assume.
Yeah, you can try to enforce it. There are papers, we've done a number of we have a number of papers trying to enforce that condition, because in some sense, this is just treating all these tasks as being independent, but we know that they are related to each other, as you were suggesting, and so you might be able to do better if you kind of tie together the losses, because you know sort of like how to go from one solution to the other solution. In practice, it doesn't seem to help a lot, but you're right. There is something called, if you could solve the Fokker-Planck equation, you could go from any score to any other score, essentially, at least in continuous time. Cool. So now we have several choices to make. We need to choose what kind of noise scales are we going to consider. So we need to decide on what is the maximum amount of noise that we're going to add. We need to decide the minimum amount of noise that we're going to add, and we need to decide how to step in between these two extremes, essentially. And for the maximum noise scale, you probably want to choose it to be roughly the maximum pairwise distance between any two data points. And the idea is kind of like if you have two images in the data, x1 and x2, you want the amount of noise to be sufficiently large so that basically it's possible to go from one data point to the other data point if you were to add noise, essentially. So if you start from data point 1 and you were to add a sufficiently large amount of noise, there should be a reasonable probability of generating a data point 2. And equivalently, kind of like of going back on the other direction. And this basically ensures that kind of like at the beginning, when you you start out your Langevin dynamics procedure with a lot of noise, that's going to mix. It's going to kind of explore the space pretty efficiently because there is a way to go basically from any point to any other point. That's kind of like the intuition for this choice. The minimum noise scale, you probably want it to be sufficiently small so that the kind of image plus noise is hard to distinguish from just a clean image. So the minimum noise scale should be very, very small. And the other thing to decide is how you go from the maximum to the minimum. So how do you interpolate between these two extremes? And again, the idea is that if you think about that Langevin dynamics procedure, we want to make sure that these different noise scales have sufficiently overlap so that when you initialize the Langevin dynamics chain corresponding to the next noise level, you're starting with something that makes sense. So if you imagine that you have these kind of spheres where you're increasingly corresponding to kind of like what you would get, or the probability sort of like as you increase the amount of noise that you add, and you go sigma 2, sigma 1, sigma 3, essentially what you want to make sure is that when you have, let's say, data plus noise level sigma 2, there should be sufficiently overlap with the kind of data points you expect when you have data plus noise level sigma 3. So that when you use the samples that were obtained by running Langevin dynamics with sigma 2 noise levels, and you use them to initialize the Langevin chain corresponding to noise level sigma 3, you have something that kind of like makes sense. Because if there is no overlap, so you go very drastic, you have like a drastic reduction in noise level. So you go from a lot of noise to very little noise. After running your Langevin chain for the large amount of noise, you're not going to get a good initialization for the next noise level. But if there is a decent amount of overlap between these noise levels, then you're kind of like, you might expect this annealed Langevin dynamics procedure to actually work pretty well. Yeah.
How can we estimate that other than just guessing?
Yeah, so we know, we are deciding how to these sigmas, right? And so what you can do is you can actually work out, a little bit of math about what makes sense, and it kind of like makes sense according to this heuristic to basically use some kind of geometric progression between the different noise levels. This kind of like ensures that there is sufficiently overlap between the different shells that you get as you increase or you decrease the amount of noise that you add. And this is a heuristic, like it's not necessarily the only valid choice, but this is sort of like the first one that we did that seemed to work. The other kind of thing we can decide is the weighting factor. Remember, we're kind of like jointly solving all these estimation problems corresponding to different noise levels. How much should we care about the different noise levels, which is controlled by this lambda sigma I kind of hyperparameter that decides how much weight do you put on the different components of the loss. And so how do we choose this weighting function? The idea is that you want to balance the importance of the different components in the loss, and a reasonable heuristic that again works well in practice is to choose that to be equal to the amount of noise that you're adding at that level.
Encourage us to like ignore like the more fine-tuning like noise levels?
It's because the size of the error changes also. The way it's scaled. Do I have it here? So the loss would look something like this, and basically, yeah, essentially you actually end up carrying the same at about the different noise levels if you do that choice. Because of the various scaling factors. So remember there is a sigma I here, so that's the, again, it's kind of like a choice. Other choices can work as well, but this is the thing that we did. Yeah.
I noticed, and similar to what I think someone asked about before, that the epsilon theta is defined as basically a scaled version of the score. Is there some like meaning behind what epsilon theta represents?
Yeah, so epsilon theta here is basically a noise prediction, because it's basically literally just estimating the noise that was added. There is different parameterization where you might want to predict, as we discussed, like kind of like when the noise level is very high, then you might want to predict the mean. So there are different ways of parameterizing this, what the network is supposed to output. This is kind of like the most, the simplest one where you're just predicting it's a noise prediction kind of task. And so the final loss looks something like this. You basically sample a mini batch of data points. Then you sample a mini batch of noise indices. So you basically equivalently choose a bunch of noise levels, one per data point. Let's say uniformly across the different noise scales that we're willing to consider. That could be maybe L here could be 1,000 if you have 1,000 different noise levels. And then what you do is you sample noise, IID one noise vector per data point. And then you basically train the score network to solve the denoising problem for each data point, essentially, with the weighting function that we had before. And and then you basically just do stochastic gradient descent on this loss, trying to essentially find parameters theta that minimize this denoising loss, which is equivalent to essentially estimating the scores of the data density perturbed with these various noise levels as well as you can. And so basically everything is just as efficient as training a single score model. Because everything is amortized and there's a single score network that is jointly trained to estimate the score of data plus noise at different noise intensities. And so the final thing looks like this. You have data, clean data, and then you have noise at the end. And so there is going to be correspondingly kind of like different versions of the data distribution that has been perturbed with increasingly large amounts of noise, going from clean data, mediumly perturbed data, all the way to data plus a ton of noise, where basically then the structure is completely destroyed. So visually, you can think of clean data, data plus a little bit of noise, more noise, more noise, more noise, all the way to huge amount of noise, where you don't even recognize what you started from.
Like in terms of noise scheduling, we always have like go from the large to small. Is that the geometry sequence we always have, or we have like different noise scheduling?
So you're thinking of increasing and decreasing and doing other things? I think in principle you could do this kind of, actually, yeah, people, I mean, you can, but not. So during learning, I guess there is always going to be, I mean, it's a scalar, and so there's always going to be an ordering, and so you're always going to be considering You're always going to go from the smallest amount to the largest amount of noise. Doing inference, it might make sense to do different things than what I described is annealed Langevin dynamics, where you would start from a lot of noise and you go all the way to clean data. There are versions where you might not want to do this, and so you might want to go from noise to data and then maybe a little bit of noise and then go back. So yeah, there is a lot of flexibility then at the inference. At training time, you need to estimate all of them, and there's always going to be a mean and there's going to be a max, and then you can kind of think about how you space them. Say again?
A parallel process training. Say again? Train them in parallel.
We train all of them in parallel, yeah. So all of them there is a single model that is jointly trained to solve all these denoising tasks. And in fact, you can get better performance if you're willing to consider multiple, like some of the state-of-the-art models that are out there, they don't have a single one, they might have a few of them. And because they can afford to train a bunch of different noise models, it might make sense to do it, because this is purely like a computational trick. If you could, it would be better to separately estimate the scores for every noise level. And so, okay, so then there's going to be different noise levels. For every noise level, there's going to be a corresponding data density plus noise, which we're going to denote P sigma 1, and this is the same as the Q sigma that we had at the beginning. So you can think of it as data becoming increasingly corrupted as you go from left to right. For each one of these noise levels, there's going to be a corresponding score model. So all these scores are going to be different because we're adding increasingly large amounts of noise. And then there's going to be a single neural network that is jointly trained to estimate all these vector fields. And the network takes the data, x, so where you are in this plot, and the sigma, and it will estimate the score for that noise level. We jointly train them by this mixture of denoising score matching objectives, and which is just a mixture of the usual score matching loss. And then we do, again, Langevin dynamics to sample. So what you would do is you would initialize your particles at random. Presumably, that is kind of pretty close to just pure noise. So we initialize our particles here, and then we follow the scores for P sigma 3, which is data plus a lot of noise. We're getting a little bit closer to the higher data density regions, and then we use these samples to initialize a new Langevin dynamics chain for the data density plus a little bit less noise. We follow these arrows again, and you see that the particles are moving towards the high probability regions of the original data density, so they're becoming more and more structured in some sense. And then we use these particles to initialize another Langevin chain corresponding to an even smaller amount of noise. And at the end, we get samples that are very close to the original data density because sigma 1 is very, very small. So this is almost the same as clean data. And throughout the process, we're getting good information, good directional information from our score models because we're using the corresponding like noise level in the data density.
It seems like more of a deterministic process. Like for a given noise level, you always get like a particular mode in a distribution. Like in a sense that if it were truly generative, you would expect like a more multimodal, I guess, code function in the sense that you should have a slight probability to go to any of the modes or any of the, I guess, the clusters over here. And I guess like that's something which I can see over here. So I was just curious, like what your perspective is.
Yeah, so that's a good question. And although the arrow is pointing you in the right, in one direction because it's deterministic, recall that Langevin dynamics is following the arrow, but it's also adding noise at every step. And so regardless of like where you are, if you run it for a sufficiently long amount of time, you might end up somewhere completely differently. So even though you initialize the particle in the same point, maybe you initialize it here, because of the randomness in the Langevin dynamics, you might end up in completely different places, meaning that you're going to generate completely different, let's say, images. And so that's the procedure, anneal Langevin dynamics. And here you can see it in how it works. This is kind of like what happens if you follow that exact procedure on real data sets. Let me play it again. So you see how you start from pure noise, and then you're kind of like following these arrows, you're following these gradients, and you're slowly basically turning noise into data. Here you can see examples on some image data sets, MNIST, CFR10, so forth, and you can see that it has this flavor of going from noise to data by following these core models. Yeah.
How many times do we update in the Langevin? Is it until it's converted?
Yeah, great question. How many steps? Ideally, you would want to do as many as possible. In practice, that's expensive, so you might want to do 1 or 2 or maybe 10. Each step is expensive because it requires a full neural network evaluation. And so that's, again, a hyperparameter. You should do as many as you can, but the more you do, the more expensive it is to generate a sample.
All the pictures are generated? Or?
These are all generated, yeah. Through the Langevin dynamics, annealed Langevin dynamics procedure. Oh yeah, so MNIST is basically a data set of handwritten digits. They kind of look like that, and then you have people's faces, and you have CFR10 samples. So these are pretty good kind of samples that were generated by this model. They have the right structure, and the model is able to generate reasonable kind of looking images. Yeah.
In training, we pick like a few discrete sigma values and fit into the model.
Yeah.
And during the inference when we anneal, can we like pick from the continuous?
So we'll come to continuous soon. Yeah. For now, yeah, it's all discrete, and you would anneal down following the same kind of schedule. Yeah.
I guess like these days you see mostly these type of models being used. So I guess like it's an objective benefit in using diffusion models compared to GANs. Like I guess more from a theoretical perspective, because we see they get better results in practice, but is that theoretically grounded for some reason?
It's not theoretically grounded. I think one key advantage is that if you think about it, they can be much more expensive at the inference time. Like imagine you're running a Langevin dynamics chain, which might involve evaluating a neural network 1,000 times, 10,000 times. So if you think of it from that perspective, you have a very deep computation graph that you're allowed to use at inference time. But at training time, you never have to actually unroll it. So that's the key insight, that you're allowed to use a lot of computation at inference time, but it's not very expensive to train because it's not trained by, like again, by generating a full sample and then checking how should I change my parameters to make the sample better. It's trained very incrementally to sort of like slightly improve the samples by a little bit. And then you keep repeating kind of like that procedure at inference time, and you get great samples. So I think that's a key insight for why.
They would both maximize likelihood, but
this is not maximizing.
Sorry, like I guess like once like I guess like they would both be equivalent, at least from some perspective, in terms of like data generation or some like matching some distribution or something. They would be equivalent from that perspective. It's just that diffusion models are at a finer scale.
Yeah, I guess they are trained in a very different way. Like there is no two-sample test. They are trained by score matching. The architectures are different. The amount of compute that you use during training at inference time are different. So there's a lot of things that change. Hard to say. There's no theoretical argument for why this is better, but in practice, yeah, it seems to be dominating. It's also much more stable to train because it's all like just score matching. So no minimax. Yeah.
So I think when you were discussing the model, there was an analogy that diffusion models are like stacking these images. How is that?
We're not yet at diffusion models, yeah. So we'll hopefully talk about that later. But we'll see the flow model soon, yeah. So if you look at certain kind of metrics that we'll talk about more in a few lectures, but it was kind of like the first model that was actually able to beat GANs that back then were kind of like the state of the art on image generation. That was kind of like the first hint that these kind of models could actually outperform GANs, despite a lot of years and years and lots of resources that were spent optimizing GANs. This thing was actually able to improve sample quality according to some metrics. And indeed, these are on different kinds of data sets. Scaling up the model a little bit, it can generate pretty reasonable faces of people and monuments and things like that. Yeah.
Is that metric, the inception, like the metrics?
Yeah, we'll talk about the metrics more in future lectures, but they're metrics that try to quantify how good the samples are, how closely they match they relate to how kind of visually appealing the samples are. And they are automated, so there's no human in the loop, and they kind of correlate with how good the samples are. Not super important what they are exactly, but the important bit was that this was sort of like the first model that was actually competitive with GANs, and that kind of like prompted a lot of the follow-up work on really scaling these models.
Yeah, so the noise level you use in sampling has exactly matched the noise level you use for training.
Yeah. And yeah, so that was very promising. And you might also wonder, which I think was also kind of like brought up here, like what does the noise levels that you use during inference have to match the ones that you see during training? Can we use more noise levels, less? And so it's pretty natural to think about what happens if you have an infinite number of noise levels. Right now we have kind of like the clean data distribution, which let's say is just a mixture of two Gaussians. So here yellow denotes high probability density and blue denotes low probability density. And then so far what we said is that we're going to consider multiple versions of this data distribution perturbed with increasingly large amounts of noise. So sigma 1, sigma 2, sigma 3, where sigma 3 is a very large amount of Gaussian noise. So that kind of like the structure in the data is completely lost. So if you start out with a distribution, it's just a mixture of two Gaussians. After you add a sufficiently large amount of noise, you're left with just pure noise, essentially. And you could imagine using, maybe here I have 3 different noise levels. You could imagine, and you can always plot kind of like these densities. And so you have, most of the probability mass is here and here because it's a mixture of two Gaussians. Then you can see that the probability mass spreads out as you add more and more Gaussian noise to the data. And now you might wonder, well, what happens if we were to consider multiple noise levels that are kind of like in between? What happens if we add a noise level that is in between 0 and sigma 1? Then you're going to get a density that is kind of like in between these two. And in the limit, you can think about what happens if you were to consider an infinite number of noise levels going from 0 to whatever was the maximum amount. And what you're going to get is an infinite number of data densities perturbed with increasingly large amounts of noise that are now indexed by t, where t is a continuous kind of random variable, continuous variable from 0 to the kind of like the maximum that you have on the right, at the other end. So each slice here, each vertical slice is basically the density of data convol, where we've added noise corresponding to this continuous index t. Right? And so you can see kind of like how I got here. We started out with a finite number of noise levels, where all the probability mass was here, and then it spreads out, and then you can think about a finer kind of interpolation, and finer, until you have something continuous. And so you go from pure data at time 0 here on the left to pure noise on the other extreme, where kind of corresponding to the maximum kind of like amount of noise that you're adding to the data. So now instead of having 1,000 different versions of the data perturbed with increasingly large amounts of noise, you have an infinite number of data densities that have been perturbed with increasingly large amounts of noise. And so you can think of what we were doing before as kind of like selecting 1,000 different slices here and modeling those data distributions. But really, there is an infinite number of them. And that perspective is actually quite useful, as we'll see. And so you have this kind of sequence of distributions. P0 is just the clean data, and PT at the other extreme is what you get if you add the maximum amount of noise, which you can think of as some kind of noise distribution where the structure in the data is completely lost, and that corresponds to basically pure noise. And so as you go from left to right, you are increasing the amount of noise that you add to the data. And so you go from pure data to pure noise at the other extreme. And now you can imagine what happens if you perturb data with increasingly large amounts of noise. What happens is that you start with points that are distributed according to P0, that are distributed according to the data density. For example, you start with these 4 images. And then as you go from left to right, you are increasingly adding noise to these data samples until you're left with pure noise. And so you can think of having a collection of random variables, xt, one for each time step, which is basically describing what happens as you go from left to right, as you go from pure data to pure noise. And all these random variables, which you can think about as a stochastic process, just a collection, an infinite number of random variables, they all have densities, PTs, which are just these data densities plus noise that we've been talking about for a while. And we can describe the evolution of this, or how these random variables change over time. If you think of this axis as a time dimension, then all these random variables are related to each other, and we can describe their relationship using something called a stochastic differential equation. It's not super important what it is, but it's basically a simple formula that relates the values that these random variables take. And it's similar to an ordinary differential equation, which would just be some kind of like deterministic evolution, where the difference is that we add basically noise at every step. So you can imagine particles that evolve from left to right, following some kind of deterministic dynamics, where we add a little bit of noise at every step. And in particular, it turns out that if all you want to do is to go from pure noise from data to pure noise, all you have to do is you can describe this process very simply with a stochastic differential equation where you're basically just the way xt changes infinitesimally is by adding a little bit of noise at every step. You can think of this as some kind of like random walk, where at every step you add a little bit of noise. And if you keep running this random walk for a sufficiently large amount of time, you end up with a pure noise kind of distribution. And not super important, but what's interesting is that we can start thinking about what happens if we reverse the direction of time. Now we have this kind of stochastic process that evolves over time, going from left to right here, you go from data to noise. Now you can start thinking about what happens if you were to reverse the direction of time and you go from capital T to 0. And so you go from pure noise to data. That's what we want to do if you want to generate samples. If you want to generate samples, you want to basically invert this process. You want to change the direction of time. And it turns out that there is a simple stochastic differential equation that describes the process in reverse time. And the interesting thing is that you can describe this process with a stochastic differential equation, which is relatively simple, and really the only thing that you need is the score functions of these noise perturbed data densities. So if you somehow have access to this, the score functions of these densities PTs corresponding to data plus noise corresponding to time t, then there is a simple stochastic differential equation that you can use to describe this process of going from noise to data. And so if you somehow knew this score function, which to some extent we can approximate with a score-based model, we can build a generative model out of this interpretation. And so the idea is that we're going to train a neural network just like before to estimate all these score models, or these ground truth scores. These are scores of data plus noise, where there is an infinite number of noise levels now. So this is exactly what we were doing before, except that now T doesn't take 1,000 different possible values. T can take an infinite number of different values. But it's exactly the same thing. Before, we were just estimating the scores of PT for 1,000 different chosen noise levels. Now we do it for an infinite number of them. And we do that by doing the usual mixture of denoising score matching objectives. So we want to be able to train a single neural network as data that jointly estimates all this infinite number of scores. And so it's exactly what we had before, except that instead of being a sum over 1,000 different noise levels, now it's kind of an integral over an infinite number of different T's. All the time steps that we have in that plot. And if you can somehow train this model well, you can drive this loss to a small number, which means that this score model approximates the true score accurately. Then you can basically plug in your score model in that reverse time stochastic differential equation. So recall we had this SDE here, such that if you knew the score, then you could just solve the stochastic differential equation, and you would go from noise to data. You take this exact equation, you replace the true score with the estimated score, and you get that. And the advantage of this is that now this is a well-studied problem. You just have a stochastic differential equation, you just need to solve it. And there is a lot of numerical methods that you can use to solve a stochastic differential equation. The simplest one is basically something similar to Euler method for ODEs, where you basically just discretize time and you just step through this equation. So this is a continuous time kind of evolution. You can just take increments of delta t, and you just basically discretize this. So I guess delta t here is negative, so you decrease time, and then you take a step here following the deterministic part, which is given by the score, and then you add a little bit of noise at every step. So you see how this is basically the same as Langevin dynamics. It's always some kind of follow the gradient and add a little bit of noise at every step. And so you can interpret that as being just a discretization of this stochastic differential equation that tells you exactly what you should do if you want to go from noise to data.
We're sampling like T samples here? How is it continuous? We're no longer kind of doing noise level by noise levels?
So there is a continuous number of them. So T is a uniform continuous random variable between 0 and T. So there is an infinite number of, let me see if I have it here. So there is an infinite number of noise levels. And what we do is we're basically numerically integrating this stochastic differential equation that goes from noise to data. So you start out here by basically sampling from a pure noise distribution. So then you take small steps. You still need to, but you have the freedom to choose. At that point, you don't necessarily have to take always 1,000th of the length. You can apply whatever. And there are many more advanced kind of numerical schemes for solving stochastic differential equations. The moment you've managed to formulate the problem of sampling to solving a stochastic differential equation, then you can use a lot of advanced numerical methods for solving stochastic differential equations. And so you step through time and you discretize, you try to find a solution to this trajectory that goes from noise to data, basically. And that's sort of like the main idea of the score-based diffusion models. And there is actually a connection with what we were seeing before we were doing Langevin dynamics. How is that related to this numerical SDE solver? You can think of it as a kind of like the numerically SDE solver will take a step. It's kind of like trying to approximate the true solution of the SDE, which is kind of like this red trajectory that I'm showing here. You can use a numerically SDE solver, and you can help it basically at every step by doing Langevin dynamics. So Langevin dynamics is kind of like a procedure that would allow you to sample from this slice. And so what you can do is you can combine, or you can just, you can either just use corrector steps, in which case basically you get the procedure that I talked about before, where you do annealed Langevin dynamics. You just follow Langevin for a little bit, and then you follow the Langevin corresponding to the next slice, and you follow the Langevin corresponding to the next slide, and so forth. Or you can apply these numerical methods to try to jump across time. And you can kind of like combine the two of them to eventually end up with something that can generate samples. So you can think of it as, once you view it from this perspective, there is, again, many different ways of solving the SDE, including using Langevin dynamics to kind of like sample from these intermediate densities that you get as you change the time dimension. And yeah, this is the kind of thing that really works extremely well. This was this kind of model, again, I guess we haven't talked exactly about the metrics, but it achieved state-of-the-art results on a variety of image benchmarks. And you can see some of the high-resolution images that can be generated by this model. These are fake samples. These people don't exist, but you can see that the model is able to generate very high-quality data by basically solving this stochastic differential equation and mapping pure noise to images that have the right structure, and I guess they're almost indistinguishable from real samples.
Possibly this question has been answered before, but I see most of the images when they have fingers in them. That's where the problem is.
They have
fingers.
Oh yeah, fingers are a hard one, to do. It's a hard problem for these models to learn how to make hands. I guess in these data sets, it's typically just the face, so you don't have to worry about it. But it's been, I think people have made progress on that as well. With more training data, I think people have been able, if you specialize, you show a lot of hands in the training set, the model kind of like learns how to do that.
Where does the awareness before we train models?
This is there is a bunch of data sets where you have like celebrities, faces, and then you can train a model there.
Pictures?
Yeah, those are real pictures.
Then use real picture and create a fake picture.
You train a model and then you generate new people that kind of look like the ones you have in a training set but don't really exist.
Is that from the real picture, which also from people's face or from other categories?
It was always faces, yeah. So you train on faces and then you generate other people's face, yeah.
So how do you validate that like the image that's generated isn't just like a sample from your training set?
Yeah, it's a great question. How do you prevent overfitting? You can look at it from the perspective of the loss. Like if you believe the square matching loss, like you can kind of see how well it generalizes to validation or test kind of data. We also did extensive tests on kind of like trying to find our nearest neighbor in the data set. And we're pretty confident that it's often able to generate new images that you haven't seen before. There are certainly cases where, especially text-to-image diffusion models actually memorize, and which might be okay. I mean, I don't think it's necessarily wrong behavior to memorize some of the data points. But yeah, people have been able to craft captions such that if you ask the model to generate you an image with that caption, it produces exactly an image from the training set. So memorization does happen, but not to the extent that it's only replicating images in the training set. It's certainly able to generate new images, including composing things in interesting ways that cannot possibly have been seen, I think, even on the internet. So it's certainly showing some generalization capabilities. And I think looking at the loss is a pretty good way to kind of see that indeed it's not overfitting. like the score matching loss that you see on the training set is pretty close to the one you see on the validation unseen data. So it's not overfitting, at least. We're not yet at that level.
So the reason why the samples are more realistic, is that because a diffusion model can estimate the true data distribution more accurate than other generative models, like a GAN or something, or is there like another reason?
Yeah, it's a mix. I can't think it goes back to what we were saying before. Like the models are trained by score matching, so it's a much more stable kind of training objective. From the perspective of the computation graph, like if you think about what happens if you solve an SDE, that's kind of like an infinitely deep computation graph. Because at this point, like you have you are discretizing it, of course, but in principle, you can make it as deep as you want. Because if you choose increasingly small kind of time steps, this can become a very deep kind of computation graph that you can use at inference time. So again, that's kind of like the key advantage, that you can have a very deep, you can use a lot of computation at inference time to generate images without having to pay a huge price at training time, because the models are trained through this score matching kind of like working at the level of small changes, kind of like figuring out how to improve an image by a little bit. And then you stack all these little improvements and you get a very deep kind of computation graph that can generate very high quality data sets.
So it's a lot like a tree, right? So is there some sort of like, you do this for some latent variables too, because you have like, you'll break down smaller.
Yeah, so latent variables, I guess I don't have time to talk about it today, unfortunately, but there is a way to think of it from the perspective of, it turns out that there is a way to convert this model into a normalizing flow, at which point you would have latent variables. And the machinery looks something like this. Like we have this stochastic differential equation that goes from data to noise. It turns out that it's possible to describe a stochastic process that has exactly the same marginals, but it's purely deterministic. So there is an ordinary differential equation, the kind of things you probably have seen in other classes, that has exactly the same marginals over time. And again, this ordinary differential equation depends on the score. So if you are able to estimate the score, you can actually generate samples. You can go from noise to data by solving an ordinary differential equation instead of solving a stochastic differential equation. And at that point, because kind of like you can think of the ordinary differential equation as basically defining a normalizing flow, because the mapping from the initial condition to the final condition of the ordinary differential equation is invertible. So you can go from left to right along these white trajectories, or from left to right or right to left, and that's an invertible mapping. And so essentially, this machinery defines a continuous time normalizing flow, where the invertible mapping is given by solving an ordinary differential equation. Like these white trajectories that are the solutions of the same ordinary differential equation with different initial conditions, they cannot cross, because that's an ordinary differential equation. So the paths corresponding to different different initial conditions, they can never cross, which basically means that the mapping is invertible, which basically means that this is a normalizing flow. And so that, I guess I don't have time to talk about it, unfortunately, but if you're willing to take the normalizing flow perspective, then you can go from data to noise, and the noise is kind of like a latent vector that is encoding the data. And the latent vector has the same dimension, because here, it's clean image plus noise, has the same dimension. It's really just a normalizing flow. The latent variables indeed have a simple distribution, because it's pure noise. And it's just like the mapping from noise to data is given by solving an ordinary differential equation, which is defined by the score model. So it's a flow model that has not been trained by maximum likelihood. It's trained by score matching. And it's kind of like you can think of it as a flow with an infinite depth. That's another way to think about it. which means that you can also get likelihoods. That's the other interesting bit that you can get if you take that perspective.